Are you ready to have your mind blown? Imagine waves, not of water, but of space and time itself, rippling across the cosmos. These are gravitational waves, and they're created by some of the most violent events in the universe, like the collision of neutron stars. But what if I told you that AI is now helping us decode these cosmic whispers faster than ever before? Is this a revolution or a potential Pandora's box? Let's dive in. We're not just talking about faster data analysis. We're talking about rewriting the rules of astronomy. The implications are huge and, frankly, a little unsettling. Think about the resources poured into traditional methods, the careers built on painstaking analysis. What happens when a machine can do it all in a second? This is the question we need to confront. The data shows that the traditional way costs 3,600 times longer. That's not a typo. 3,600 times. This changes everything. Neutron stars. They're the incredibly dense remnants of massive stars that have exploded as supernovae. When two of these bad boys collide, they create gravitational waves and a brilliant explosion called a kilonova. These kilonovae are cosmic forges, producing heavy elements like gold and platinum. The problem is, these events are rare and fleeting. To catch them, we need to be fast. Really fast. Imagine trying to photograph a hummingbird with a flip phone camera. That's how challenging it is to observe these kilonovae. And that's where AI comes in. But is this speed worth sacrificing accuracy? Are we so eager to catch a glimpse of these cosmic events that we're willing to trust an algorithm over years of scientific expertise? This is the debate raging in the astronomy community right now. You have to consider the sheer amount of computation power this saves, the time gained. It's not just about speed, it's about unlocking new discoveries. But at what cost? The trade-offs are real, and they're significant. At the heart of Decoded is a neural network, a complex system of interconnected nodes that learns to recognize patterns in data. In this case, the data is the gravitational wave signal emitted by merging neutron stars. The neural network is trained on simulated data, allowing it to quickly identify and characterize real-world signals. The key is that the neural network can perform this analysis much faster than traditional methods, which rely on computationally expensive simulations. Think of it like this. Traditional methods are like trying to solve a puzzle by brute force, trying every possible combination until you find the right one. A neural network, on the other hand, learns to recognize the shape of the puzzle and quickly identifies the correct solution. We are talking about Bayesian inference here. This method allows the AI to quantify the uncertainty in its predictions, providing a more robust and reliable result. This is crucial for making informed decisions about where to point telescopes. The use of convolutional neural networks, CNNs, allows the AI to automatically learn hierarchical features from the raw data. This eliminates the need for manual feature engineering, saving time and effort. You can check it out at the Nature Journal. The team published the paper Real-Time Inference for Binary Neutron Star Mergers using machine learning. But there's a catch. Neural networks are only as good as the data they're trained on. If the training data is incomplete or biased, the neural network will produce inaccurate results. This is a major concern in astronomy, where the data is often noisy and incomplete. Can we really trust an AI to interpret data that we ourselves struggle to understand? This is the fundamental question we need to address. Why is real-time computation so important? Neutron star mergers emit not only gravitational waves, but also visible light and other electromagnetic radiation in the subsequent kilonova explosion. To observe these signals, telescopes need to be pointed at the right location as quickly as possible. The faster we can analyze the gravitational wave data, the greater the chance of catching the kilonova. Jonathan Gare, a group leader at the Max Planck Institute for Gravitational Physics, points out that current rapid analysis algorithms used by the LIGO-Virgo-Cagra collaboration make approximations that sacrifice accuracy. Decoded addresses these shortcomings by fully characterizing the neutron star merger in just 1 second without making such approximations. This allows for a 30% more precise determination of the sky position. Imagine trying to catch a firefly in the dark. The faster you can react, the better your chances of success. That's the same principle at play here. This is not just about observing a kilonova. It's about understanding the fundamental physics of neutron star mergers. By observing these events in detail, we can learn about the equation of state of neutron star matter, the formation of heavy elements, and the nature of gravity itself. But what if we're so focused on speed that we miss subtle details in the data? What if we're so eager to make new discoveries that we overlook potential errors in the AI's analysis? This is the danger we need to be aware of. The stakes are high, and the pressure to publish new results can be intense. We need to ensure that scientific rigor is not sacrificed in the pursuit of speed. Here's where the debate gets really interesting. On one side, you have scientists who argue that speed is paramount. They believe that the potential for new discoveries outweighs the risk of minor inaccuracies. They point to the fact that Dingo BNS can improve the accuracy of sky position determination by 30%, allowing for more efficient use of telescope time. On the other side, you have scientists who prioritize accuracy above all else. They argue that even small errors in the AI's analysis can lead to misinterpretations and flawed conclusions. They worry that relying too heavily on AI could stifle creativity and critical thinking. Think about the early days of photography. Some artists dismissed it as a mere mechanical reproduction of reality, lacking the artistic vision of a painting. But eventually, photography became an art form in its own right, opening up new possibilities for visual expression. The same could be true of AI in astronomy. It could be a powerful tool for discovery, but only if used responsibly and with a critical eye. One point of contention is the use of event-adaptive data compression, a technique used by Dingo BNS to reduce the size of the data while preserving the essential information. While this technique can speed up the analysis, it also introduces the risk of losing valuable data. This is a trade-off that needs to be carefully considered. We have to remember that this technology is still in its early stages of development. There are bound to be glitches and limitations. The key is to acknowledge these limitations and work to overcome them, rather than blindly accepting the AI's output as gospel. The future of astronomy may depend on our ability to strike the right balance between speed and accuracy. What does this AI breakthrough mean for the future of neutron star research? Alessandra Buonanno, a director at the Max Planck Institute for Gravitational Physics, believes that Dingo BNS could one day help to observe electromagnetic signals before and at the time of the collision of two neutron stars. Such early multi-messenger observations could provide new insights into the merger process and the subsequent kilonova, which are still mysterious. Imagine being able to witness the birth of a kilonova in real time, capturing the first moments of this cosmic explosion. This could revolutionize our understanding of how heavy elements are formed and how gravity works in extreme environments. This is not just about neutron stars, it's about understanding the fundamental laws of the universe. By studying these extreme events, we can test our theories of gravity, probe the nature of dark matter, and learn about the origins of the cosmos. But let's not get carried away. AI is not a magic bullet. It's a tool, and like any tool, it can be used for good or for ill. It's up to us to ensure that it's used responsibly and ethically. We need to be aware of the potential biases and limitations of AI, and to use it in conjunction with human expertise and critical thinking. The future of astronomy is not about replacing human scientists with machines. It's about empowering them with new tools to explore the universe in ways we never thought possible. So what do you think? Is this AI breakthrough a game changer or a potential threat to scientific rigor? Let me know in the comments below. And don't forget to like and subscribe for more updates on the latest AI breakthroughs in science and technology.